Okay, so we've done several examples of doing Laplace analysis on circuits with, analysis with Laplace transforms on circuits. Let me maybe phrase that a little bit better. Um, the next thing we're going to talk about in these lessons are something that's referred to as the transfer function. And quite frankly, this is in my opinion, the real reason we want Laplace transforms for circuit analysis. It's not really to look at a circuit and just analyze it like we did instead. It's to get a transfer function. And so let's go ahead and just define what we mean by a transfer function. A general definition, so this is the most general definition here, is that a transfer function is y at s over x at s. And here, y at s is equal to the output and x at s is equal to the input. Now, common ones here, so common transfer functions, or commonly used, that doesn't look right, I don't think there's two N there. Is there two L's? Why am I trying to worry about spelling so much? Okay, commonly used transfer functions would be the following here. We have h at s being some output voltage over some input voltage. Or another common one is that we have some output current over some input current. Now those are probably the two most common ones that you would encounter, but there are applications for other ones, and the other ones that you might see would be where, well, we'll still look at the output voltage, but in this case we'll look at, instead of it being the input voltage, we'll look at being the input current. And the transfer function here, the other one that you might look at would be an output current over an input voltage. Now if we think about the units here, this has no units because it's voltage over voltage. This has no units because again it's current over current, so amps over amps. Technically, if we think about this, this is volts over amps, so this is going to be a unit of ohms, and this would be ohm to the -1, or which is equal to capital S, which is really a Siemen. Now, again, the most commonly used ones are the ones that have no units here. Now, we could use any of these, but the ones we're going to be examining in these next couple videos here are going to be the V out. Actually, probably in the next couple videos, I'll be honest, we're probably only going to be looking at this V out over Vn, which is the most common transfer function that we're going to look at. Alright, so let's look at an example here for this and see why we might be interested in doing this. So we're going to do a very simple example to start with here. And so we're going to look at here, I'm going to have a circuit with a voltage source, a resistor, an inductor, and then a capacitor. And we're going to look at the output being the voltage across the capacitor, and the input is going to be simply this voltage source. And then of course we're going to have a resistance R, L, and C for the capacitance. Alright, so let's maybe go ahead and pick some real numbers here to see what we can get here. So just one second. Okay, so the component values we'll do here, I paused it just to come up with some component values here. We'll just do a 4 ohm resistor, a 1 Henry inductor, and a 1/4 farad capacitor. Now again, the reason I'm choosing these numbers is just to make it work out nicely for us. We don't have to use these pretty of numbers. In fact, we'll look at an example where the numbers aren't as pretty. So if we look at this here, if I want to know what V out over V in here is, we should think at this and look at the circuit, and hopefully we can see here really quickly that all we're going to need to do is voltage division. And if I do voltage division here, well, maybe I should be careful. Before I do voltage division, I should do the Laplace transform of everything. So 4 ohms stays as 4. This is going to go to just S, because it's S times L. And this is going to go to 4 over S, because it would be 1 over S times C, so that would be just 4 over S. All right, so now let's go ahead and do voltage division here. So I would have that V out is equal to 4 over S divided by 4 plus S plus 4 over S times V in. And now when we have that here, we can see getting the transfer function here is actually somewhat trivial, because to get the transfer function, we get V out over V in, because we just divide both sides by V in, and we get then that the transfer function is 4 over S over 4 plus S plus 4 over S. Now, just like we normally would do here, we're going to clean things up here. And to clean things up, I'm going to multiply by S over S. And so my transfer function becomes 4 over S squared plus 4S plus 4. Now, obviously I rearranged the terms here, because if I do S times 4, that's 4S, and then S times S is the S squared, the 4 over S times S is the 4. So I just wrote it in descending order here. Now, one thing that we're going to be interested in, and we'll explain why in a little bit later here, is we're going to be interested in something called the poles and zeros. Well, in order to know what the poles and zeros are, first off, let's just go ahead and remember, this is actually just from algebra. Poles are S values that make denominator 0, and then zeros are S values that make the numerator 0. So if I look at that, whoa, sorry about that. So if I look at that here, I have my transfer function of h at s is equal to 4 over s squared plus 4s plus 4. So what we want to do is, in general, you're going to want to factor these as much as possible. And the denominator, and I picked these numbers out on purpose, the denominator factors to just s plus 2 quantity squared. Now, if we think about what we have here, the zeros, so we're looking at what makes the numerator 0, the s values that the numerator makes 0, well, there are none, because we have just 4 sitting in the numerator. So it doesn't matter what you plug in for s, the numerator is never going to be 0. But then we can clearly see that the poles we have would be s equals -2. And we'll go ahead and write here It's not required to do this, but it will be important in other courses. Multiplicity 2. And that just is because it's repeated twice. So the multiplicity, let me just emphasize here, this gives us the actual pole. This gives us the multiplicity. Okay, so great. So we have our transfer function. What's the big deal? Okay, well, let's continue on with this example some more, and then in the next video we'll look at a more challenging example problem. So what I want to do here is we're going to do two questions now here. We're going to do part A, find V out when V in is equal to 5u at t. And then part B is going to be find V out when V in is 3 cosine of 10t. Now, the nice thing about this is that we don't have to do two separate circuit analysis problems here. I mean, we have two problems we have to solve, but we've actually characterized this circuit completely. We have all the information we need to know about the circuit. And what do I mean? In other words, is that V out in both cases is just going to be simply my transfer function times V in. And that's because my transfer function was defined as V out over V in. So for part A, V out at S would equal four over S plus 2 quantity squared times, and then I have to think about what the Laplace transform of 5u at t would be, and that would simply just be 5 over s, which looks like I wrote 5 over 5 there. 5 over s. And so I just multiply this by 5 over s. Now, I'm actually not going to multiply everything out because I'm going to multiply the numerator and get 20 over, but I'm not going to multiply the denominator out. And you think about, why would I not multiply the denominator out? Well, if I'm going to try and find V out at t, which is what I want to get eventually, well, we're going to have to do a partial fraction expansion. And so why multiply the denominator out? Because then we just have to factor it again. So that's important to remember here. It's also why we actually like to have the transfer function factored, is because then whenever you multiply by the input, you'll be able to do the partial fraction expansion just pretty much right away. Now, I'm not going to actually do this partial fraction expansion. This one's pretty straightforward. We've done this in several other videos. I'm going to do it for part B here. Now again, instead of having to do an entire new circuit analysis here, I just have to recognize that, hey, this is now gives me a Laplace transform of s over s squared plus 100. Now I'm going to pause it because I'm doing that by memory and I just want to double check. And double checking that is the correct Laplace transform. So V out would simply be 4 over s plus 2 quantity squared times 5 over s squared plus 100. I'm sorry, 5. My s there looks like I got just sidetracked there. It would be s over s squared plus 100. Now again, I'm not going to factor this out at all, because then my V out is simply 4s over s plus 2 squared times s squared plus 100, which partial fraction expansion is going to give me a over s plus 2 plus b over s plus 2 quantity squared plus cs plus d over s squared plus 100. Now this partial fraction, I know it's going to make the video a little bit longer than I like to make them, but that's okay. I am going to go ahead and do this partial fraction expansion for us. So we'd have 4s is equal to a s plus 2 times s squared plus 100 plus b times s squared plus 100 plus cs plus d times s plus 2. Now I don't know if these a, b, and c and d are going to be nice numbers here. I picked it to be nice numbers for the denominators here. So one kind of obvious, quote, smart number for us to pick would be s equals -2. Because that would make this first term 0. The second term won't be 0, but the third term will be 0. So we'd have -8 is equal to b times -2 quantity squared plus 100. Which, if we do the arithmetic for that, we would get -8 is equal to 104b, which, yeah, it's definitely not going to be a very pretty number. That will, of course, reduce for us a little bit. And I'm just using my calculator real quickly to do that. So we get -1/13 is equal to b. Now, you might say, oh gosh, there's no other nice numbers to pick. Well, this is where you can be a little clever, and you might say this isn't a nice number to pick, but actually it is. I mean, we can just pick random other numbers, but we have still quite a few things that are unknowns at this point. Well, let's think about this for a second. There's a couple things we can do here. First off, instead of picking another nice number, let's think about some things here. I'm not going to multiply this all out here, but I'm just going to look at here. And if I were to multiply this out, foiling and everything, the highest degree term would be s cubed. Right? Because I'd have an s times s squared. So I'd get the highest degree term as s cubed. Here, the highest degree term would be s squared. Here, the highest degree term would be s squared. So I'm going to wind up with, on the right-hand side, the right-hand side is going to have an as cubed. It's going to have a lot of other stuff there, but it's going to have an as cubed. That actually helps me figure out what a has to be, because as cubed has to be equal to 4s. Now I'm going to write this out a little bit in more detail so you can, I think, make sure it's 100% obvious. As cubed, in other words, has to equal 0s cubed plus 0s squared plus 4s plus 0. So what does that mean? What's in front of the s cubed here? A equals 0. All right, awesome. So we've gotten rid of that term completely. So I can just kind of cross this off and ignore it now for the rest of the computation. In fact, I can cross it off here because that's going to be gone as well because a is now 0. All right, but now there's even another kind of clever thing you can do here to figure out, well, actually, no, we already have what b is. I'm sorry. Clever thing, it's not that clever, is we can see I have a c times s. If I do s equals 0, Well, then I'd have 0 is equal to negative 1/13 times, well, it's going to be 0 squared plus 100, so times 100. But then c times 0 is going to be 0. So it'd be d times 2. Oh, well, that gives me right away here, assuming I don't mess up my arithmetic, d is equal to 50 over 13. So let's just double check that. 100, negative 100 over 13 gets added to the other side. I divide by 2, so yes, I get d is equal to 50 over 13. Now I have one last number to find, and yes, you've all guessed it correctly probably at this point, and that's where we're going to use s equals 1. And then we'd have on the the left-hand side, of course, we just have 4. On the right-hand side, remember, I don't have to worry about a because that's 0, so that whole term's gone. So I have negative 1/13, negative 1 over 13, times 101 plus c plus 50 over 13 times 3. And then we just solve this. And I'm going to pause it while I solve it here. And going through the work here, I get c is equal to 1 over 13. Okay, so then let's see here. I know this one's actually this is like twice as long as what my videos are normally, so I apologize for that. Oh, I need to scroll back up here just to make sure. Okay, so I have negative 1 over 13 times 1 over quantity s plus 2 squared. And then I'm going to, it's cs plus d. So I'm going to factor out that 1 over 13 in the front, and then it would be s plus 50 over s squared plus 100. Because I just factored the 1/13. In fact, I'll factor the 1/13 out in front of everything. So this is v out at s. So I'm going to factor the 1/13 out in front of everything at this point. And do a tiny bit more work here. So I have 1 over 13 times negative 1 over s plus 2 quantity squared. But then I'm going to write this as s over s squared plus 100 plus 50 over s squared plus 100. Now, why am I breaking it apart like that? Well, let's think about this. Cosine of omega t goes to s over s squared plus omega squared, where sine of omega t goes to omega over s squared plus omega squared. So if I think about this, what do I need here? I need this to be a 10. So that's actually pretty easy to do. I'm going to erase this as 50, and I'm going to write a 10, and then I'm just going to have 5 times that. And now I have it in a perfect form to do the inverse Laplace transform of this. So Vn, not Vn, what did we just find here? Not Vn, we found V out. V out at S is negative 1 over 13 t e to the minus 2t plus 1 over 13 cosine of 10t plus, what am I doing here? I had factored those 1 over 13s out in the front here. You're probably all screaming at me right now. What are you doing? No, it's not cosine omega t, it's cosine of 10t plus 5 times the sine of 10t. And then again, remember, we should always multiply this by u at t at the end. All right, so yeah, a lot of work involved here on the partial fraction expansion. But as far as, like, if you want to think about level of difficulty as far as partial fraction expansion, this is probably what I would consider one of the more difficult partial fraction expansions that you'd be expected to be able to do on an exam.